Hello everyone. In our last session, we were talking about increasing and decreasing functions and how to find the open intervals where the function was increasing and decreasing. So in this session, we are going to be talking about the first derivative test. So let's start first with the monotone functions. A monotone function is a function which is either strictly increasing or strictly decreasing on the entire interval. For example, you look at this x cubed function, it is strictly increasing throughout. Okay? Or for a decreasing function, we can have something like this. So this is f of x equals negative x cubed. Or you can have a function which is, say, a function which is a straight line which goes down. That's again entirely monotonic functions. Now, the example of not strictly monotonic, suppose we have a piecewise function where the function is increasing from negative infinity to 0, then it is 0 from 0 to 1, and then from 1 onwards it is increasing. So clearly it is not monotonic because you will increase, then you just rest down for some time and then you again go up. So the monotonic functions are another set of functions. We will see that why we are talking about that in a short while. Okay, now let's begin with the first derivative test. Now, what is the first derivative test? To do the first derivative test, I'm going to first start with a little example and then, include the theory. So let's look at this function. We have seen that function before. This was a function which was a cubic function, and we used this to find the open intervals. Remember, the function is increasing from negative infinity to 0. And over here, notice the derivative of the function is positive. And then from 0 to 1, the function is going down. And if you would look at the derivative of the function, it is negative. And then from 1 onwards, the function is increasing. But we had 2 points, which were the points which you could see as the hill, which is at the point 0, 0, and at the point 1 and minus half, you all have a relative minima. Okay, so notice in this relative maxima what's happening. At this point, the function first increases. So here's my function increasing. At the maxima point, after it has reached the maximum point, the function starts to decrease. That's where you will see a relative maxima happening. Okay? And notice when the function is increasing, the derivative of the function is positive. Where the function is decreasing, we know that the derivative of the function at any point here is negative. Okay, now when you have a relative minima, what you notice? That the function is first decreasing and then it increases. So the point of relative minima shows the function to decrease first and then increase, whereas the point of maxima shows that the function is first going to increase and then decrease. So that's the idea for the first derivative test. Okay, so let's talk about the first derivative test. Now, if c is a critical number of a function which is continuous on an open interval I, say containing this critical number, now if f is differentiable on this interval, except possibly at c, it's okay if the function is differentiable, then we can classify the following. If the derivative of the function changes from negative to positive at c, then we say f has a relative minima at the point c and f of c. If f prime of x changes from positive to negative at this point c, the function has a relative maximum at the point c and f of c. If the function is positive on both sides of c or negative on both sides of c, then the function at c is neither a relative maxima or a relative minima. So graphically you can see it over here. the first derivative test, if the function is having a relative minima, notice the graph goes down, that means the derivative is negative, then the derivative becomes positive. On the other hand, for relative maxima, the function is increasing, that means the derivative is positive, and the derivative goes down, that's negative. If it is neither relative minima or maxima, you can see the graph keeps on going up or the graph keeps on going down. Okay, so we have done our theory. We will now start with examples. Let's look at the first derivative test on an example we did earlier when we were looking at the intervals for increase and decrease. Now, remember this function x plus 9 over x. And if you remember the graph was like, remember x is a point where the function is, not defined, rather it's, it's a vertical asymptote at that point. So that means the y-axis, notice, is a dotted line, and the graph goes like this. Okay. We talked about that this was the point where the change of the graph from positive to negative. So these were the open intervals we were talking about. Okay, so now let's go ahead and look at the points here. Now we want to find this point. And we want to find this point. Okay. Now we notice the x is plus minus 3, which is the critical numbers. But remember the 0, x equal to 0, the y-axis is where the function is undefined. Okay. So we have to include that in our test interval. And what we found was we found a test intervals, if you remember. I'm going to show you a little thing. I just remember I always draw a little, number line, a little visual aspect of it. So I had -3 and I would create my little critical number, graph here, and then we would pick up test values in between this interval. But remember we had, 0 as the point, and we were using a triangle to represent our 0 as the point of discontinuity. So we had now 4 test intervals: -infinity to -3, -3 to 0, 0 to 3, and 3 to infinity. Notice when we plugged in the values, we looked at the sign of the derivative of the function at -4. Now remember, the derivative is what? Let's look at the derivative. The derivative is 1 minus 9 over x squared. So what is f prime of -4? So f prime of -4 is 1 minus 9 over 16, which is a very small number. And on top of that, it is positive. So the function is increasing. That means this part, the function is increasing. Then from -3 to 0, the function is decreasing. In other words, when you put 1 minus of, so here f prime of n is what? 1 minus of 9 over 1, which is basically -8. Function is decreasing. It's decreasing. Again, the same thing happens from 0 to 3. Function is decreasing. And then function increases. Okay. Notice, when a function increases to decreases, so this is increasing, this is decreasing. So we have this little thing. So what I normally do is, I go according to the arrows. The function increases, the function decreases. So I have a maxima at -3. There's nothing going to happen at 0 because it's decreasing and decreasing. Notice this is decreasing and this is decreasing. Okay, then from 3 to, so from 0, this interval, so you notice the arrow, it decreases and then it increases. So that this point, which is 3, is the point of minima, and -3 is a point of maxima. So clearly, on this little visual representation, I was able to, just by the arrows, I was able to get the points where the function has a relative minima and a relative maxima. So then we applied the first derivative test, or you can do it over here also, the maxima and the minima. So we conclude that the function has a relative maximum at the point. Remember, when you write it down, this basically means minus 3 f of minus 3. You plug in the value here, 1 minus 9 over 9. So f minus of 3, f of x, sorry, it's 1 plus 9, so it's minus 3 plus 9 over minus 3, which is negative 3, negative 3, negative 6. And similarly, the function has a relative minimum by this first derivative test at the point 3 and 6. Okay. Now, let's go to the next function, an example which we have already done when we were looking at the open interval. So we already have all the required values done. So we're just going to go ahead and apply the same rule, just the first derivative test. Now remember, this function is the nice little sine curve. So if I draw this curve from 0 to 2 pi, remember this is how the graph goes. So this is from 0 to 2 pi. This one is pi halves. And this one is 3 pi halves. Okay? So clearly, function increases from 0 to pi half, decreases from pi half to 3 pi half, and 3 pi half to 2 pi, it increases. So we found the critical numbers. You can go and look at the notes, in the earlier session. And that's a value for pi halves and 3 pi halves. So when we look at this little table, from 0 to pi half, you see this one? Okay, so the function is increasing. Then function is decreasing from pi halves to 3 pi halves. And then function again is increasing from pi halves to 3 pi halves to 2 pi. So if I want to see, clearly I know that this is the maxima and minima. But if I can go according to my directions of just following the arrows, so this pi half is where the function has a maxima, and then I go according to the arrows from downwards to upward. So 3 pi halves is the point where the function has a relative minima. Now pi half and 0. Remember, what is f of pi halves? That's the value here. It is pi halves and f of pi halves. What is f of pi halves? Sine pi halves minus 1, 1 minus 1, 0. What is 3 pi halves? So f of 3 pi halves is sine of 3 pi halves minus 1, minus 1, minus 1, negative 2. And that's a value where the function has a relative minima. Okay, now these were the function examples we had done earlier. Now let's pick up another example and we will start from scratch over here. Okay, let's look at this one. Find the relative extrema of this function x squared minus 2x plus 1 over x plus 1. Now, the moment you look at the function, you see that at x equal to minus 1, the function is not defined. That means that's a point of discontinuity. Okay, so we already have that in our minds, discontinuity at minus 1. Okay, now to find the critical numbers. That means I'm going to take the derivative. So remember it's u over v. So f prime is what? V squared u prime v minus v u prime. So when you do the math, what you get is x squared plus 2x minus 3 on the numerator. You can easily factor it. You have x plus 3 times x minus 1 over x plus 1 squared is 0. So for this derivative to be 0 to get the critical numbers, that means the numerator has to be 0. So what are my critical numbers from here? X is minus 3 and 1. Now, so they're going to be 3 points, and that means we'll have 4 intervals. But 2 of them, remember minus 3 and 1 are critical, whereas minus 1 is the discontinuity. That means that's a point where you basically have a vertical asymptote. Okay, let's look at the graph of this function also. So we'll have an idea. Remember, I'm using the desmos.com, which I've shown it to you, and you can use that to also make your life simpler. So you have an idea what's going on. So this is the graph of this function. Notice the graph at -1, you notice this is -1. So this graph is like a vertical asymptote. You don't see any kind of, the graph will never cross it. But this is the point of minima, which is exactly at 1, which we know we have a critical number. So that means the critical number at 1 is a point of minima just from the graph. And the graph at -3 is a point of maxima. You see over here? This is -3. See -3 and -8, 1 and 0. So you can see those points over here. Now, we are actually going to apply the first derivative test, and this exactly will be shown over here too. So it's a nice way to look at the graphical representation and have an idea. But when you show it, when you do it by hand, all this, you have to apply the first derivative test. You have to show every step. That's important. Graphs just convey the, it just makes sure that whatever you are doing, it is going to make sense. But it's important that you should know how to apply theory and understand theory too. Okay, guys. So we have got this. Now let's create our test intervals. Okay. So remember here, x equal to -3 and 1. So remember what I normally do? I actually create my little number line. Now -3 is my critical number. So I draw. So this is my visual way of looking at how things will go. Now -1, remember, is the discontinuity, and I'm just representing discontinuity in my head as a little triangle. And then I have 1, which is my critical number. So when I do the math, I already know, oh, what's going on. So now looking at this nice little number line with little, rectangles and triangles, which basically convey something which gives me the interval. So one interval is from -∞ to -3. The next one would be -3 to -1, then -1 to 1, and then 1 to infinity. We already have seen graphically how the result would look like, but we would like to make sure the first derivative test also mimics that too. So here's it. Now, what we notice, we have to pick up some test points. Remember what is the symbol we use? We did a little cross over here, -4 across -2. These are test values which will tell us whether the function is increasing or decreasing. Then a 0 and then 2. Now, once we have got those little test values, we will evaluate the derivative at -4. You plug it in. Remember f prime. So this was the function. What is your f prime? Okay, let me just get the value here. So what was our f prime? Let's write it down here. So f prime was x squared plus 2x minus 3 over x plus 1 the whole square. So when I'm putting f prime of -4, I'm basically plugging in the values in this little right-hand side of the equal sign. And we get the value to be 0.5556, which is positive. That means function is increasing. Then we pick up -2, the value is -3. Function is decreasing. At 0. Now from -1 to 1, that will pick up a test value 0, -3, again it is decreasing. And when f prime of 2, it is increasing. So what do we notice? When we apply the first derivative test, what do you notice? I go by the arrow, and so I go up at critical numbers, that's when it is 0, derivative, it is 0. And then you go down, nothing is going to happen, -1, because remember both the values before and after -1, they're decreasing, and rather this is a discontinuity. You cannot cross the graph over here. But when you go, from -1 onwards, then you see the graph goes down and grows up. So that means this is the point of maxima, whereas 1 is the point of minima. So what we see, function has a relative maximum at the point -3, -8. Guys, remember, this is f of -3. And that is the original function. Which was the original function? Original function was x squared minus 2x plus 1 over x plus 1 the whole square. And it has a relative minimum at the point 1 and 0. Notice the graph. The point -3 and -8 and the point 1 and 0. Okay? Now let's try one more example. This is a trig example. Okay, so we are going to look at this, find the relative extreme of this function applying the first derivative test. The function is half x minus sine x from 0 to 2 pi. Let me show you the graph here. This is the graph of the function. It dips down, then goes up, then again dips down. So it's dipping down at 5 pi thirds. After 5 pi thirds, it dips down. And at pi thirds, it's the minimum. You can see just from the graph, you have an idea. Okay. Now, let's go ahead and apply the theory. Remember, that's what you will be showing. You can make sure that when you use the Desmos to do your work, it actually just conveys it shows that what you're doing is right, but you will have to show all these steps when you're working on your, assignments. Okay, so the first thing is, because this is a nice little continuous function, no problems, no discontinuities or something. So just go and find the critical numbers. When you take the derivative, this is half minus cosine x. Cosine x is half. So there are two places where the cosine x is half. One is pi thirds and the other is 5 pi thirds. Now these are going to make our test intervals. So here's our intervals of increase and decrease. You go from 0 to pi thirds, pi thirds to 5 pi thirds, and pi thirds to 2 pi. As usual, you know what I do? I actually make a nice little number line. And first one is pi thirds, critical number, starting as 0. 5 pi thirds, another critical number, and then 2 pi. So if you go from 0 to pi thirds, that is one test interval. Second test interval is pi thirds to 5 pi thirds, and then 5 pi thirds to 2 pi. Now we're going to look at our test values. So pi thirds, I'm going to pick up pi fourth. Now from pi thirds to 5 pi thirds, easy values pi, and 5 pi thirds to 2 pi's is 7 pi fourths. So you evaluate the derivative function at pi fourth. Now remember, what's the derivative of the function? F prime of x was what? Half minus cosine x. So f prime of pi fourth is half minus cosine pi fourth. So it is half minus cosine pi fourth, which is basically half minus root 2 over 2. And you do the math, you get negative 0.207. Now when you put in f prime of pi, that means half minus cosine pi, which is half of plus 1. So it is half minus cosine pi, which is half plus 1, 3.5, 1.5, and similarly f prime of 7 pi fourths is a negative 0.207. So clearly, the function is increasing from the interval 0 to pi thirds, then it decreases from pi thirds to 5 pi thirds. Oh, sorry, I just said the opposite, sorry. Oh, sorry, it was the opposite, sorry guys. Okay, from 0 to pi third, the function is decreasing because it's a negative. Then pi thirds to 5 pi thirds, it's increasing. And then 5 pi thirds to 2 pi, it's decreasing. So when we look at the first derivative test, so it is a relative minimum at pi thirds and a relative maximum at 5 pi thirds. And then this, guys, remember, is the value of the function f of pi thirds. Remember what's the original? It's half x minus sine x. So it's going to be half pi thirds minus sine pi thirds. Then you can just do the math. Oh, it's 5 pi thirds. Sorry, this one. Okay. Now, once we have done a lot of these, first derivative tests, and now we're going to look at another question. This I'm going to do with you. It's an example. It's not a practice. It's an example. This one is basically the understanding of the concepts of what we have learned so far about what is the meaning of critical numbers, what's the meaning of increasing, decreasing functions, and looking at the graph, how you can figure out whether it has a relative maxima, minima, or neither. Okay, so let's start with the first thing. We're given a graph which is a quadratic function. Now this is a graph which is represented by f prime. It's an f prime graph. Okay, so it's important, guys. Remember, differentiable functions are functions. Okay, so this differentiable function, this function, is basically a quadratic function. Now we're going to look at understand the concepts. What is the meaning of critical numbers? Critical numbers means where f prime is 0. As this is the graph of an f prime of f prime. F prime, remember, is a function. Okay, keep in mind f prime is a differentiable function. Okay, let me just talk a little bit about this, which will help you what I'm saying. So when I say, let's look at this one. I have a graph fx, which is say x cubed minus 2x. So when I take the differential of this is what? 2x squared minus 2. Now this is also a graph, right? F prime. I could just have shown this, say, suppose this is k of x. It doesn't matter. I'm just writing down that this is a differentiable function. So that's what it means. F prime is a differentiable function. Now, remember, the original function was cubic, but the derivative is a square function. So when I draw the graph, now cubic function, x cubed minus 2x. So what would be x cubed minus 2x? So let's use our Desmos to do the work for us, okay? So it's x. Let me just show it to you. Give me a minute, guys. Okay, here's the function. X cubed minus 2x. Okay, now when you differentiate, so clearly this is a cubic function, you see that. So if I differentiate, I'm going to do it right now and show you how the graph looks like. It's, 2x squared minus 2. So notice the graph of this differentiable is 2x squared minus 2. The original graph, which was here, was in black. That's x cubed minus 2x is the original graph. That's the cubic function. But the differentiable function is a squaring function. Okay, so they are actually functions. So we will be combining things what we have learned in our algebra class, the meaning of a function, with what we are learning here in the calculus class. So now this is going to be a combination. That's where the concepts are being tested. Okay, so I hope this is much more clear to you guys. Now let's come back. So this one is the idea that f prime is a differentiable function. Okay. Now, when I say f prime is 0, now that's the definition of a critical number. Now in terms, because now f prime is a function, so where is the function 0? The function is 0 in terms from the understanding of the meaning of a function. Where is the function value 0? Remember what he says, f prime of x is 0. That's what this is the definition of a critical number. F prime of x is 0. Now we are given a graph. We do not know if we can figure it out how to find the what is the equation part of it, but we don't need to do that. We are just going to rely on our understanding of what is a function. Okay, so when I say my f prime of x is 0, now let's look at it from a functional point of view. What does it mean? It means, suppose if I said this was k of x. So that means what are the values of x where the function value is 0? So if you notice, in terms of graphical, it is where it is crossing the x-axis. This is a point x and k of x to be 0, or f prime of x to be 0. That's the meaning. So those are our critical numbers, because critical numbers are the value are the points where the derivative is 0, and we are given the graph of the derivative of the function. So what are my critical numbers? Now looking at the graph, the critical numbers are x equal to 0 and 1. That's 1, that's 0. That's where I get my critical numbers. Okay, now let's draw our little number line. Remember, I always draw a number line because I'm more visual, as I said. A 0 and a 1. Now, the next part of the question is identify the open intervals where the function is increasing and decreasing. Now, what we learned, when the function is increasing, the derivative is positive. So this is the scenario where you see the derivative is positive because it is above from the graphical point of view. Okay, this is a graph of f prime. Every value of f prime over here above the x-axis is positive. So that means this is the scenario, anything which is less than 0 on the x, but the value of the function is positive. So that means here f prime is positive. That means the function is increasing here. Now from 0 to 1, what is happening? The derivative values are negative because this is a graph of f prime. Keep that in mind. I'm combining things what I know from the literal meaning of what is a function to what we are learning in terms of derivatives. So that's a nice combination happening here. Okay, so here from 0 to 1, notice what's going on. The derivative is negative. Okay, the derivative is negative just from the graph. It's a graph of f prime. Okay, that is, it has negative values. That means the function is decreasing. That is, it's going down. The original function, remember, is a cubic function, because if your graph of a function is quadratic, the original function is going to be 1 degree more than that, which is going to be cubic. Okay, now once again, when you go beyond 1, the function is positive. So we already have our critical numbers. So this is our critical numbers. We found the critical numbers. Now the open intervals where the function is increasing or decreasing. So the function is increasing from negative infinity to 0 and 1 to infinity. Where is the function decreasing? 0 to 1. Okay, now let's look at things whether the function has a relative maxima or minima. Now two critical numbers. So let's do the normal thing we do. As this is a critical number, I make my little box, a rectangle, and enclose it in a rectangle. Now, to find a relative maxima minima, that means we'll apply the first derivative test, FDT. Now, what happens before 0? Function goes up, then the function goes down. That means the function has a relative maxima at 0. But I do not know what is the value of that function. I just know it is 0. Then the function is decreasing. It goes down and then it goes up. That means the function has a relative maxima at x equal to 1. So let's write it down. The function has a relative maxima at x equals 0. Remember, I'm not writing the point because either I find out the original function. If I am unable to do so, I'm just going to say x equal to 0. This is the original function, not this function. This is f prime. That's the derivative of this function. And it has a relative minima at x equals 1. And that's how you do these problems. This is a very, very conceptual, and this is where you are making connections of everything you have learned so far in mathematics. Okay, so once we are done with this, guys, what we do next? We do some practice problems. Okay, so please, guys, do these practice problems. Apply the first derivative test to find the extrema of these functions. Thank you.